and share my screen again. Okay, so the participant numbers are still rising up, so we'll just wait another minute or so just for them to flatten out. But yeah, thanks again everybody for joining. This is the first of a two-part Space-Enabled Net Zero by 2050 webinar, and it's I think now the fourth or fifth in our Emerging Technology webinar series with the Satellite Applications Catapult and the University of Glasgow. So Amanda, I'll hand over to you to kick things off, and I'll stop sharing my screen to allow you to start sharing.
Fantastic. Hello, everybody. Can I just check if you can see the screen okay? Yeah, fantastic. So hello, everybody. Welcome to the Space-Enabled Net Zero by 2050 event. My name is Amanda Campbell. I am the head of Net Zero at the Satellite Applications Catapult.
Sorry, Amanda, we can't quite. I can't see your screen at the moment.
No,
sorry.
You can't. Sorry, let me do it again. I check that you can all see it now. Yes, participants can now see your screen. Eddie, jump in unless there's something going wrong there. Thank you. Okay, fantastic. So yes, I'm Amanda Campbell, head of Net Zero at the Satellite Applications Catapult. So first of all, what is net zero? So net zero is essentially an accounting perspective, and it's the balance of anthropogenic emissions of greenhouse gases, and we need to balance them by 2050. And so we need to get a, sorry again. So net zero emissions is about the balance of greenhouse gas emissions, and with the aim of limiting a warming to 1.5 degrees. And the reason why we need to achieve 1.5 degrees Celsius is to, sorry, I'm got a bit of a stutter, sorry about this. Be fully aware that we need to limit warming to 1.5 degrees, and in order to do that, we need to balance our emissions. Across the globe, we've got significant commitments coming across. 90% of global GDP is covered by net zero commitments, which is significant. And you've seen the commitments coming out of the national disturbance contributions from countries. So we've got commitments across the globe and across the private sector as well. Net zero is, net zero about limiting to 1.5 degrees. We need to halve our emissions by 2030, and we need to be compensating between that and sorry, could you just give me 2 seconds? Pause for a second. Apologise. Sorry, I don't know what's going on there.
That's okay.
Something's going on in the background. It is very critical that we align our targets with science-based targets. The Science-Based Target Initiative, which provides the frameworks and the pathways in which we need to go to. It's when you think about not only the global emissions and cutting targets, you can also think as your the companies and the organizations that you work in and the challenges you have there. So if you think about your company, how are you going to halve your emissions by 2030 and achieve zero across the full scopes of scope 1, 2, and 3? It's very critical as well that we are compensating, investing in activities to them and focusing on greenhouse gas removals. What have satellites so far done for net zero? So over 60% of the essential climate variables are measured exclusively from space. So the space and satellite data has directly fed into the policy and the findings from the IPCC to drive the change and the commitments which we've seen at COP. However, the capabilities and the applications are continuously evolving. So we have new data sets and new metrics and new satellites going up with improving the capabilities. We also have more precision and more evidence. So by having more data sources, we're able to, by having more evidence, we are able to get more of an understanding of what's going on in the emissions and provide and essentially have more truth in aspects of that. We're also increasing the processing capability, so we've got more accurate predictions, and we're increasing the accessibility of them. So really need to emphasize as well that the role of satellite in climate science has really driven the policy. We've seen significant movement, but now it's predominantly about the applications, getting the already existing data into more hands, more business users, so it can drive decisions there. Moving forward, what is the potential for satellites and what can they do for net zero? So the focus of this talk is about Earth observation and monitoring. Climate science and environmental monitoring has been prevalent in the data and the policy, but predominantly in informing the decisions. Satellites also have a role in the connectivity. So we're talking about efficiencies and the data and being able to share the scope 3 emissions data across improving those areas. And finally, navigation, location. So when we're looking at value chains across different companies, you can use satellite data to observe, identify them, and bring them and identify and actually monitor where they're going. And so you can have a lot of an understanding of where the movements of your materials to understand scope 3. It's really critical that satellites play a role really in every sector, and there's evolving technologies, and it's not just satellites in isolation which will drive the solution for net zero. They're an enabling technology. So often a lot of the solutions, satellites are one key part of it, and it's supporting. And it's also key to know that there are solutions for satellites across pretty much every industry. So every industry, every sector is working on net zero and how to achieve the compliance and the regulations, and satellites can play a role in every part of that. Earth observation is the focus of the talk today, and Earth observation is about gathering information about Earth's physical, chemical, and biological systems. So to summarize, in the context of space and net zero, over half the essential climate variables are measured from space. So satellites have played a prevalent part in driving net zero policy. It provides an unbiased evidence to inform decision makers. And we're also in a very unique position to support and drive climate action. So what I really want to drive in the focus of the talk today is what I really want to drive today in the talk is understanding what technologies and what are the applications that are currently happening to drive net zero in the space sector. Also to think about the gaps and the challenges. When you think about how your business can achieve net zero, what are the monitoring challenges from understanding your supply chain? How do you know that the data you're collecting is accurate? How can you prove on the accuracy? And a big part of this is about collaboration, sharing data, sharing expertise. And the Catapult is committed to facilitating and supporting companies with this and bringing them together. So thank you very much. I will stop the video there and okay, fantastic.
Brilliant. Thanks for that introduction to the webinar, Amanda. So we'll hand over to Colin to chair our only session now. Thanks, Colin. Over to you.
Yep, thanks, Amanda, and thanks, Eddie. So good morning, colleagues. Thanks for joining the next in the series of emerging technologies webinars organised by the Satellite Applications Catapult and the University of Glasgow. I'm Colin McInnes. I'm with the Space and Exploration Technology Group here at the University of Glasgow. So to kick off the webinar this morning, we've got 5 short presentations from ESA, academia, government, the Satellite Applications Catapult and industry, followed by a panel discussion, which will be chaired by my colleague, Dr. Giles Bailey. So please add your questions to the chat as we move forwards, and then Giles will pick up some of the questions during the panel discussion after the 5 short talks. Okay, so just to move straight ahead, the first talk is from Dr. Clement Abergel, who's a climate applications scientist at ESA, the EXAT Centre. So I will hand over to Clement.
Thank you very much. I will try endeavor to share my screen. I assume you can hear me well, and that now you can also see my screen.
Yep, all good.
Perfect. So yes, thank you very much. Good morning, everyone. Thank you very much for the introduction and for having me this morning. Yes, I'm Clement Abergel, and I am with the European Space Agency Climate Office, where I develop climate applications related to land surface. Very briefly, our main objective at the Climate Office is to implement the ESA climate program, the climate change initiative. That main objective is to develop global scale, long-term, robust, satellite-derived time series of key components of the climate system. You will have understand I'm talking about the essential climate variable as introduced by Amanda. So this talk is the opportunity for me to give you a broad overview of the ESA climate change initiative. If needed, I will try to convince you further that space data are essential in the net zero context, and I will illustrate how some of the data set we produce under our climate change initiative can be used. But first, let me give you some very brief background. So, satellite Earth observation have the capabilities to contribute to achieve the main goal of the Paris Agreement for Climate in many ways. And that can be through further effective policy making and or policy implementation monitoring. As part of the Paris Agreement, all parties agreed to a global stock take every 5 years, starting next year in 2023, to assess the collective progress towards achieving the purpose of the agreement and to inform of further individual actions to be taken by parties. Parties have to report the greenhouse gas inventory every year, their emissions and removal. And they are also required to submit their anthropogenic emission reduction goal as part of their national determined contribution, NDC, every 5 years. So we can feel here that there is a strong need to develop ways to monitor progress. In their reporting, national emission inventory agencies are mostly using bottom-up approaches, combining activity statistics with emission factors. Very little use is made of satellite Earth observations, only by a handful of countries, including the UK. That is probably also because yet we do not have Earth observation data that quantifies greenhouse gas fluxes directly. Rather, there are observations of variables or proxies that can be transformed into fluxes using models. Earth observation can also be used to improve the emissions factors used by national agencies for their inventory. But bottom line is we need to use satellite Earth observation to support improvement of countries' emission inventory. This can be through top-down atmospheric inversion, combining greenhouse gas measurement in situ, satellite and atmosphere transport model to backtrack a concentration from a source, or bottom-up with process-based GGVMs model or bookkeeping approach that can be constrained by Earth observations. The capabilities of Earth observation satellite in support of climate information needs reflect the unique abilities and benefits. They have wide area observation capabilities, are non-intrusive, provide uniformity, rapid measurement, and continuity. And that is precisely why the role of the European Space Agency is crucial to climate and climate actions. ESA has been dedicated to observing Earth from space ever since the launch of its first weather satellite back in 1977. And this slide illustrates the Earth observation mission we have developed over time and the whole range of submissions that will come in the next decades. Today, satellites are used to forecast the weather, answer important Earth science questions, provide essential information to improve agricultural practices, maritime safety, help when disaster strikes, and all manner of everyday application. With the launch of a range of different types of satellites over the last 40 years, we are better placed to understand the complexities of our planet, particularly with respect to global change. And the need for information from satellites is growing at an ever-increasing rate. And with ESA as world leader in Earth observation, the agency remains dedicated to developing cutting-edge spacebound technology to further understand the planet, improve daily lives, and support effective policy making for a more sustainable future. Back to climate now. It is in response to the UNFCCC requirements for systematic monitoring of the climate system that ESA has launched its Climate Change Initiative research program back in 2010. So CCI is a coordinated research and development program amongst ESA member states that generate robust, long-term, global satellite-derived data set for key components of the climate system, the famous essential climate variable ECVs. And these ECVs, as Amanda said, are specified by the GCO, the Global Climate Observing System, and support not only the climate information needs of the UNFCCC and IPCC, but also the wider climate community. And the CCI does this by harnessing ESA Earth observation archives generated over the last 40 years and combining them with data from third-party and the current missions, including the Copernicus Sentinel mission. I think one of the latest third-party missions to be brought in is Greenhouse Gas Sat. I'm sure that it will be mentioned in other talks this morning. Under CCI, we currently have 24 dedicated ECV projects, developing 22 ECVs. And as you can see on this slide, each of these projects addresses a specific variable in the oceanic, terrestrial, and atmospheric domain. We also have a dedicated climate modeling user group to foster more links between the Earth observation and modeling community. And we have a research fellowship program. All our data sets are freely available on our open data portal. And finally, on top of that, we also have cross ECVs activities, such as a sea level budget closure project, and perhaps closer to us this morning, the Recap 2 project on regional carbon budget. And those projects combine the information from multiple ECVs to answer specific questions. And I will now use 2 slides to illustrate first a specific ECV project, and then the Recap 2 cross ECV project. I could have used the greenhouse gas CCI project. However, the next speaker may mention it as well. No pressure. So instead, I will illustrate the fire CCI project and a rather interesting recent finding from them. So it is estimated that about 25 to 35% of greenhouse gases result from biomass burning, and therefore they are considered an important factor in climate change. The fire CCI project focuses on the key variables burn area, and it has different products at global scale and, let's say, moderate and core spatial resolution, derived, for example, from MODIS from the beginning of the 2000s, then Sentinel-3, and even before using AVHRR. But not only. It has recently focused on high resolution at regional scale, for now, using Sentinel-2 information at 20 meters spatial resolution to develop a small fire database covering for now only sub-Saharan Africa and for 2 specific years, 2016 and 2019. And this slide illustrates the small fire dataset. As you can see here, for a plot over Africa, the 20 by 20 meters footprint of Sentinel-2, the image at the bottom right-hand side of the slide, made it possible to detect way more fires compared to the 500 meter or 250 meter spatial resolution of global product previously used. The image you have at the top. So over Africa, and for 2016, 90% more small fires were detected with the Sentinel-2 product than with a lower resolution MODIS product. And they contribute to nearly half of the total burn area detected. As you can imagine, the corresponding fire carbon emission from African fires are clearly higher than previously thought. And this is a substantial increase. Small fires are a critical driver of burn area in sub-Saharan Africa, and including them in emission estimates raise the contribution of biomass burning to global greenhouse gases and aerosols. Recap 2 now. So the ESA CCI Recap 2, as I said, it's a cross-ECV project that objectives are to evaluate the feasibility of producing updated estimates of greenhouse gas balance at country level, constrained by Earth observation, by satellite Earth observation, using an ensemble of top-down atmospheric inversion and bottom-up land surface model. Also, they want to improve their consistency against official estimates reported by countries to the UNFCCC. They have been working directly with several national inventory agencies, including based in the UK, to provide greenhouse gas information that matches user need. And so this information can go beyond the sphere of research. So during the first phase of the project, the team has designed and implemented a comprehensive framework to process the results of atmospheric inversions in order to make them suitable for evaluating the estimates of anthropogenic emissions and removals of greenhouse gases made by UNFCCC national inventories. And this work represented a major achievement from a technical point of view, combining a large number of heterogeneous data sets from various providers, and from a scientific point of view, reconciling process-agnostic inversions with more process-oriented inventories, despite different definition of greenhouse gases variable. On this figure, you have the CO2 fluxes for land sinks and fossil emissions for the main emitters on the x-axis, and the box plot represents the inversions for different time periods. In red, you have the fossil fuel, and in green, you have the land sink. The black horizontal lines symbolize the net CO2 fluxes for inversions, while the circles represent the mean of UNFCCC national greenhouse gas inventory data, what countries are reporting. And there is a striking consistency between the mean for each period of national greenhouse gas inventory land carbon sinks and inversions for all major emitters. And this verification of national inventory reports against atmospheric inversion results paves the way for countries to improve checks and consistency of national inventory to reflect global emissions more accurately. And this approach also improves transparency in the accounting process and facilitates the effectiveness of mitigation policy and progress by individual countries to meet their pledges as part of the Paris Agreement for climate. Right, looking to the future now, 6 Sentinel expansion missions are now foreseen to address policy and gaps in Copernicus user needs and to expand the current capabilities of the Copernicus space component. And these missions are a direct reaction to the most pressing questions for which we need reliable information from a policy, research, and economy side. And in the context of this webinar, I would like to highlight the CO2M mission, which will deliver source-driven information on CO2 emission, so we can finally quantify emissions and also attribute them to their sources. CO2M will be Europe's first operational CO2 mission and will enable monitoring anthropogenic CO2 emissions to assess the effectiveness of the Paris Agreement and COP21 decisions. It will make it possible to assess the overall CO2 budget at country, regional, and also mega cities scales. And the raw CO2 observations will be complemented by NO2, aerosol, and cloud observation. And finally, this slide is to give you a brief comparison of CO2M capabilities in terms of coverage and sampling with respect to other already existing or foreseen mission, with London somehow used as a reference. And as the next talk is focused on greenhouse gas monitoring from space, I will not go further into details. And with that, I would like to conclude my talk. Thank you for having me, and I apologize that I need to go almost straight away to join another meeting. Thank you very much.
Thanks very much, Clement. We'll just move straight over to our second speaker, who is Professor Hartmut Bosch, Divisional Director for the National Centre for Earth Observation and Head of the Earth Observation Science Group at the University of Leicester. Just before I hand over, again, to remind people, if any questions, please drop them into the chat box, and we'll pick up all the questions at the panel discussion. So I'll hand over to Hartmut. Thank you.
Okay, thank you very much. Yes, and I think it was good to get this really fantastic introduction into the topic by Clement. And I was fearing that he would, my fear was he would cover all the greenhouse gases already, but quite fortunately, he saved it for me. So I will talk about greenhouse gas monitoring from space. So what we of course want to achieve is that we want to limit the rate of the buildup of atmospheric CO2 and also methane and other greenhouse gas in the atmosphere. So as already said before, this means we really need to control and verify emissions associated with human activities. And ideally, we also want to understand and exploit natural processes that we can also use. What this really means is that we really need to be able to measure it, because we can only manage what we can measure. And it's well known that emissions, they leave an atmospheric signal. For example, at the bottom, you can see signals that are related to burning of fossil fuels and power stations. So they result in this very small but noticeable signals in the atmosphere. However, of course, in addition, we also have many signals, very strong fluxes from natural sources and sinks. And we have weather effects, which will transport all these signals around, which we need to disentangle. So this means we are faced with a very complicated measurement problem that we need to solve. And we have three main satellite resources that we can currently use, which I quickly want to introduce. So the main workhorse is really the GOSAT and GOSAT-2 instrument, which is from JAXA. So these were the first dedicated greenhouse gas sensors launched. So they give us this fantastic global picture going all the way back to 2009. More recently, we have also seen the launch of the first NASA satellite called OCO2, which is focused on CO2 only. Again, it has very much this global focus. So it has relatively small pixels on the ground, but it has a very narrow swath. So essentially, there will be quite some data gaps in between. A little bit of a game changer is the TROPOMI mission, which was launched in 2017 by ESA. So the big difference is that TROPOMI, in contrast to the predecessor missions, has global coverage. So essentially, it has a very wide swath and gives us really this continuous global coverage every day. So this is really very different to OCO and GOSAT. So essentially, we have these three fantastic data sources that we can exploit, but really these satellites are primarily designed to give us global climate data records, which are then contributing to initiatives like the ESA Climate Change Initiative and now also to the Copernicus Climate Change Service. And essentially, thanks to these great initiatives, we have now put together these data records, which extend effectively more than 20 years. And anybody who's interested in it, you can actually very easily obtain these data sets. And the key element of these programs is to not only generate these data sets, but also to verify the accuracy and to document them. And a key purpose of these data sets is that they are contributing to this global flux inversions, for example, in recap initiatives. And there's quite some success now of linking this back to large country or subcontinental scale fluxes, and also you can also try to make some effort to link it back to emissions, as we've seen by previous speakers. But the reality is that our current satellites, they are really not ideal for emissions. For example, the OCO2 instrument, as is seen here, has this very narrow swath of only 10 kilometers, which is mapped by about 8 measurements by the satellite. So this really means that essentially you need to look for a needle in a haystack if you want to see specific emission signals, but it's possible. And there has been quite some good success. What I show, for example, here is where it has been possible to detect signals that are related directly to power stations. So essentially you can see the power station is highlighted with this yellow mark. Then you can see the downwind emission signal that directly relates from the emissions of the power station, which is typically a signal of around a couple of parts per million out of 400 parts per million. So we get our first glimpse of what we can do with satellites. Of course, we can also look at satellite observations over cities. So a very good example is Los Angeles, which is at the bottom here. So the nice thing about Los Angeles is that we have this, again, this very narrow satellite tracks that go over the cities, but also for Los Angeles is where we have a desert, so we have a very clean background, and we can simply look at the contrast, which is shown on this time series. And again, what we see is that even a mega city like Los Angeles only produces emission signals which are around 2, 3, 4 parts per million out of 400. So these are relatively small signals, but they are well observable, but they're also very variable because of variable metrology. So this is something that we need to take into account. And these measurements, they are clearly challenging our current abilities with models. But of course, we don't only have these satellites, there are also some quite novel satellites. There's an instrument called OCO3, which is essentially spare parts of the OCO2 mission. So this has been installed on the International Space Station. And with these satellites, there is no attempt of doing global monitoring. Instead, there is a pointing mirror. And thanks to this pointing mirror, we can actually have this special snapshot area mode, where for the very first time, we can map out over a somewhat restricted area of 80 by 80 kilometers, essentially CO2 over a city. So this is quite unique and is really the very first time we can really see the CO2 distribution across a city. And what this really shows us essentially is that we see these intra-city signals, which we can exploit. Again, they're on the order of 1 to 6 parts per million. So they're very small, and also they're very variable again. So again, having the right modeling approach is absolutely key and is something that we need to foster and further develop. Now we are quite fortunate that we are quite fortunate that also we will have a dedicated European mission, hopefully very soon. So this mission is called Microcarb and is supposed to be launched end of 2023. So this is a mission that has been developed by the French space agency CNES, but the UK has joined as a mission partner in 2017, and we are actually now contributing hardware and software. And very importantly, we will have the ability to also influence where the satellite will measure and what the satellite will do, which will give the UK a great advantage. And now Microcarb, this mission has also a global focus, but it has also a special city mode, which is quite similar to what OCO3 can do. So essentially it has a mode to map out a city with relatively small pixels and very high coverage. So here you can see the example of Los Angeles, but of course you can imagine that we can do exactly the same measurements, for example, over London, which will be really very powerful so that we can develop systems that can constrain city scale emissions. Okay, I just want to say a few words about methane. So for methane, we are actually further advanced than for CO2, and there are many reasons. One is that anthropogenic or emission signals for methane are much stronger. There is not the same strong biogenic signals involved that have fluxes in and out of the surface. So essentially, it's a little bit a simpler problem to solve. And what we can see here are just two examples. One is focused on the US and one is focused on India, where you can really see the power of satellites to inform on these national scale emissions. So on the top, you can see the top figure shows our best estimate of emission inventories. And at the bottom is after we also use satellite data. And on the right-hand side, you can actually see how satellites have changed this emission inventory, where there's a need to really upscale the emissions very substantially over areas of strong oil and gas and also of intensive agriculture. A very different picture is actually found for India, which is quite interesting. So here we can find that actually the standard inventories are overestimating emissions that we see with satellites, but with here for the very first time, we could actually use also satellites to verify that the reporting to the UNFCCC is in very good agreement with satellite observations. Now, this is all done with our earlier GOSAT instrument, and the newer TROPOMI instrument is actually greatly enhancing this ability to infer national scale emission inventories. There are also some really new emerging capabilities which really help us to verify emissions. And for methane, we have now many imaging satellites which allow us to directly look on individual emission sources. And this goes all the way from TROPOMI, thanks to its imaging capability, but also we can now use a whole host of different hyperspectral satellites that can measure these emissions on, can map out these emission plume really on tens of meter scales, which is really unique. And here are just some examples from TROPOMI where you can clearly see the enhancements over Polish coal mining areas. But then we have new satellites like GHGSat, where you can really pinpoint to individual emission facilities, which I think is really unique. Okay, and finally, I just want to say where we are moving to, and like already mentioned by Clément, this is really operational systems. So now we are in a process of developing these operational systems to directly support the Paris Agreement, and the space component of this system that is developed in Europe is called CO₂M. So this will really be a game changer. So what CO₂M will deliver is essentially it will map out the whole world with 2 by 2 kilometer pixels every 3 days. And essentially the idea is that the swath is sufficiently wide that you can capture a whole city in one go. And this allows you then, of course, to really use this observation to directly constrain emissions from the city. What is quite important that there are also additional tracers built in, for example, NO2, which is a tracer to identify anthropogenic emissions. And there are also specific aerosol information that allow us to make this data much more accurate. Okay, and I just have one summary slide that really gives an outlook on what's coming next. So it's quite clear that satellites provide us some of these key global data sets on CO2 and methane. In the future, we will see much further enhanced capabilities, but also quite a significant diversification. We will see geostationary missions, we will see active LiDAR missions, and we have a very large portfolio of very high resolution satellites, which are often also commercial. But quite importantly, I think satellites clearly will provide key support capacity for monitoring and verification of emission reduction policies, for example, like the operational system that is based on the CO2M mission. And I think that's it. Thank you very much.
Thanks, Harwood. We'll move straight on to our third talk, which is from Dr. Elisa Strouds, Earth Observation Policy Lead at DEFRA. So I'll hand over to you, Elisa.
Thank you. I'll just share my screen just a moment. Can you see that okay?
Yeah, looks good, thanks.
Right, thank you everyone for inviting me to talk today. I'm Elsa Stroud, I'm Head of Earth Observations Policy, and I sit in the Office of the Chief Scientific Advisor in DEFRA. So what I'm going to give today is more of a user needs perspective, particularly from a key user of Earth observations in policy. I'll just set out here that DEFRA aren't the lead department on net zero, and so I can't give an overall government view here, but what I'm going to give is our perspective on meeting DEFRA's particular net zero agenda, what we need from the technology, and other sort of co-benefits or serendipitous activities that also help support DEFRA's activities here. So the UK, just before COP, launched its net zero strategy last October, with COP being in November in Glasgow. It cites the role of Earth observation quite heavily there. And Amanda earlier on was very right in her introduction, where she said that every sector has a responsibility here. And this strategy recognises how the pandemic's allowed a reset of a lot of industrial processes and dives into our key polluting sectors. So the ones in bold written here are the responsibility of my department, DEFRA, along with adaptation as a whole. And I know net zero doesn't strictly cover adaptation, but I'm going to cover a little bit about Earth observation for adaptation anyway, taking that remit. The UK has demonstrated its backing to this strategy with a series of spending review commitments. We've just started a 3-year spending review. So we have a 1 billion net zero innovation portfolio. And for my department, 75 million has been made available for research innovation for these particular sectors. Just a bit of the policy lines, as I'm sure a lot of you are key users of Copernicus data, and DEFRA is the Copernicus policy lead. So our position here is really that we will strive to remain at the forefront of Earth observation technology and know-how in the UK. And this is because it's so important in our ambition to be a science and technology superpower and to lead in both tackling climate change, but also biodiversity loss, key to DEFRA's agenda. The UK does remain committed to association in the EU programmes, including participation in Copernicus, but the EU aren't honouring the commitments that were made when the Trade and Cooperation Agreement was agreed. We did choose to participate in Horizon Europe, Copernicus, Euratom and Fusion for Energy because they do represent a real benefit to British people and our industry, and that does still remain our goal. However, because of this delay, we are considering how we might alternatively support that Earth observation capability in the UK in line with our national space strategy ambition. So on to EO for mitigation in DEFRA's sectors. Here we show some a land use cover map that's been developed in DEFRA's Earth Observations Centre of Excellence, which brings together expertise from all our arm's length bodies and delivery agencies. And this map is updated regularly, that shows particularly the carbon sequestration potential and activity across the whole of England, and is updated on a regular basis and used in models for land use change and carbon sequestration potential within DEFRA. In the UK, networks for monitoring greenhouse gases are significantly less extensive than that for air pollutants, and that's partly because of different mixing ratios and the ability of these pollutants to mix and be globally representative rather than locally representative. And mostly they're designed for measuring local pollutants such as roads, particular farms and other pollutant sources. We're using Earth observations at a relatively early stage, I must say, to look at air quality and greenhouse gases together and look at the potential for understanding what are the basket of other emissions that are sometimes more representative in DEFRA sectors. For example, nitrous oxide, the global warming potential of nitrous oxide is about 265 times greater than that of carbon dioxide on a 100-year timescale. Natural sources account for about 2/3 of those emissions, but we do emit quite a bit from fertilizer processes. 70% comes from agriculture, 7% comes from waste management, and 7% from land use. So that's one we're particularly keen to keep an eye on. I'm showing here also ammonia, which is a key agricultural emitter, particularly from pigs, poultry, those sort of areas. We are looking particularly at particular policy interventions that can reduce ammonia emissions, and this shows us really how much that has changed in recent years. One that I've not shown here, and one that we're particularly interested in, would be F-gases. So if there's a new emerging potential to look at fluorinated gases, because they have a global warming potential of up to 17,500 times that of carbon dioxide in 100 years. And DEFRA is responsible for that. So if anyone's particularly interested in measuring F-gases from space, then I'm particularly interested in hearing from you. Over to peatland mapping and condition change. This is more work of our Earth Observation Centre of Excellence, and this was an exploratory assessment of using Earth observation in monitoring the condition of the UK's peatlands. So the primary aim was to classify the peat condition attributes, which allows us to predict the contribution that peatland makes to the UK's greenhouse gas emissions inventory. And actually it's changed from being considered a source, a sink of CO2 to being actually a source in recent years because of the poor condition a lot of this peatland is kept in. Now, if we can reverse that, then we can turn it back into a sink again and potentially can contribute to net zero. This has been focused on 4 pilot areas, particularly in Scotland, which represent the most extensive and poorly characterised ecosystems. So we're really looking at improving the resolution, frequency, and interaction with other condition factors, such as catchment sensitive river catchments, to better understand how we can support on peatland mapping. We also look at burning of our upland areas. This is a project that we looked at on Island of Skye, which looked at temporal change, predicted burns, and ground truthing of upland moorland burn against a Google Earth backdrop. This project helped you explore whether radar and satellite imagery can be used to continually update maps of burning UK environments. So that's a combination of satellite, radar, and in situ data to understand the impact of wildfires and muir burn on carbon emissions, but also on biodiversity and how we account for this in our natural capital. So once complete, this radar map will inform the scale, distribution, and frequency of activity, the damage caused by wildfires, and to inform good land management practices and behaviours that could be promoted to reduce the likelihood of or the impact of such fires in the future. A lot of this all feeds into our role in natural capital and ecosystem assessment, which has a huge team in DEFRA, many of which have moved over into the Chief Scientist's office recently. And it's the role Earth observation plays in our way of ensuring ecosystem services and natural assets are considered in economic evaluations or policies, which is underpinned by the NCEA. So taking any environmental policy, be it to improve our waters or protect priority habitats, you can see how we need Earth observation, but in combination with other tools and processes such as historical data, models, and ground truthing, to really understand what the objective of that policy should be, but also to understand what the other pressures going on, and crucially, whether the policies are working as they're intended to do. I'm just going to touch briefly on Earth observation for adaptation, not strictly being part of the net zero agenda, but really key part of DEFRA's mandate. So we support GeoGLAM, which is a global agricultural monitoring program through the Intergovernmental Group on Earth Observation, to the tune of about 100 million a year in official development assistance. And GeoGLAM looks at the mandate for food security, not just in the UK, but internationally. It's focused on particularly food insecure countries and a range of crops that are regionally important for food security, and follows the pressures and the resulting yields that are anticipated from those. So since 2016, GeoGlam has also been working with LDCs, low developing countries, to co-develop their own national monitoring systems, and this has been proven to be really successful, which turns programs into policies around protecting particular crop types and assessing threats, be they security threats or climate change adaptation threats. And this is developing into supplemental guidance for the UNFCCC National Adaptation Programme process to help scale up the use of crop monitoring for early warning as a climate adaptation response. Some emerging areas that we're particularly interested in, and I'd be keen to hear from the audience around, is around illegal disposal of building waste, which we know is developing particular interest in the Earth observation community. We're also interested in looking at things like marine littering, so the larger scale plastic pollution under the OSPAR Convention. We're looking at the validation that Harmet spoke eloquently about in terms of its complexity in bringing these column concentrations down to contribute towards emissions validation, because that's really where we want to get to in understanding where these emissions are coming from. And also aspects of how we can use Earth observation in law, in legislation, and in legal challenge. I'm just going to highlight here some of this work that was presented back at COP, and you can still watch this online. This was Earth Observation Day, which was used to set out how the UK is really working towards improving reporting, tracking and measuring of sectoral, regional, national greenhouse gas emissions. There was a whole host of excellent contributors you can see on the right, and it really talked about how we can use this in our adaptation support as well. So in conclusion, satellites really provide an extraordinary insight into our climate and environment, and able to us to understand and monitor how it's impacting Earth. We will really strive to remain at the forefront of Earth observation technology and know-how, because it supports our ambition to be a global science and technology superpower and to lead the world in tackling climate change and biodiversity loss. So DEFRA particularly is a key user of EO data, and our ambitions can be really as broad as validation, legislative compliance and source attribution. So we'd really encourage you to think about that wider DEFRA remit when you're considering your technological application. But really, to engage the public and legislative processes in EO data, we really need trust, inclusivity, a systems approach that considers these multiple pressures on environmental systems, and space for innovation. So that's my final remark. And just to note that this is actually my last day in DEFRA, and I'm moving on to a new role in Environmental Standards Scotland, where I'll be holding the Scottish Government to account on their environmental practices. So I've left you there with my team email address here in DEFRA if you need to get in touch with any of my team in my absence. Thank you.
Thanks, Ailsa, and good luck with your new post with the Scottish Government. So we'll move on to our fourth speaker, who is Dr. Christian Rossi, Geospatial Science Lead at the Satellite Applications Catapult and visiting lecturer at the University of Oxford. So I'll pass over to Christian.
Thank you. Share my screen. Presentation mode. All right. Thank you for the introduction. Let me first acknowledge the co-author of this talk, which are several, and you see listed here, and also the organizations that are associated to those, which are the Satellite Applications Catapult, the University of Oxford, the Alan Turing Institute, and Astrea. Today I'm going to talk to you about the use of Earth observation into the finance sector, and specifically about spatial finance. So what is spatial finance? Spatial finance is the integration of geospatial data and analysis into the financial theory and practice. We see an example here. I try to use the pointer. Yeah, it works. So we got several stakeholders here, such as the government. The government basically create policies such as net zero policy and pass these through other stakeholders, such as investors that they own companies, and companies that they own assets. Now, assets that are both on the natural and built, characteristic, and they're exposed to different risks, such as climate risks. Now, spatial finance, the sweet spot of spatial finance is in here. So it's in providing observational data, such as data that we have seen in the previous talk, within this framework. And part of this data can be used also to for this asset, for the asset, what we call asset level data. So to provide several parameters that are associated to those assets. Now, those sort of parameters, they are sometimes existing. So companies are releasing sustainability parameters in form of company disclosures. But there are several challenges here, since those parameters, they're not really homogeneous. If we translate this into ESG framework, we can see in this plot here 2 different ESG scores on the 2 axes here. We would expect them to stay the same, so basically to have that's a scatter plot, so to have like a straight line here, but we see how this is very much dispersed. That means that this reporting is not standardized and data is not comparable. So how can we support this? We can support this clearly with observational data and with remote sensing, with Earth observation. So we see, and we have seen also previously, how the number of satellites, in this case more satellites, is exponentially increasing, and the number of data, the amount of data that we have is really huge. We see an example here over China of nitrogen dioxide emissions. So this is from Sentinel-5P, and we see the impact of lockdown in the middle. So we're here, where we got a decrease in nitrogen dioxide. Now, spatial finance, it's used within this context now. So to provide data that is like timely and comparable, so and as well neutral, and it's an objective source of information, such that we can connect financial system with the real economy. Now, in financial institution or financial organizations, we are seeing actually an uptake of data analytics in general, but there is still several data that is missing when we think about assets. So let's look at this table here. So we have the availability of asset level data in the x-axis, and the level of emissions here. So we got high emissions to low emission, and no availability to basically almost all data is available. So we got several sectors here which are with no data available, and few sectors, mainly on power, where we have like the majority of data available. Today I'm going to focus on a specific asset, which is cement here, which has a very high emission. It's one of the major actually source of pollution when we talk about industrial assets. And this is actually part of a framework, so which is called geo-assets. So we built what is called Spatial Finance Initiative, which is part of the new UK Centre for Greening Finance and Investment, and as a core partner, the Oxford University, Alan Turing Institute, and the Catapult. So the objective of this framework is to provide this data, asset level data, for free. So this data is completely accessible, and you can actually download it in the link that is here. So at the moment we got iron and steel, but the plan is to enrich this with many more assets in the future. Now, I mentioned I'm going to talk about cement. I'm entering a bit more technical in the technical aspects now. So and specifically on the use of artificial intelligence in defining these these assets. So we see the architecture here that we used to derive the database. This is actually a pretty much a standard deep learning architecture where we get data sets that they get clean. We generate models, deep learning models. We deploy model. There is actually another step, which I'm going to explain later, on collective intelligence and the derivation of the dataset. So this is pretty much a standard architecture. As you recall from my table, cement is actually is partially available. Data is partially available about cement. So, and it's partially available through, for example, OpenStreetMap and the global cement directory. So what we have done is that we have taken the location of existing assets with these two databases, and we verified in Google Earth the coordinates. And we added on top of it some information such as capacity, production here, and ownership with the PermID database. So this is basically our training dataset. So when we run deep learning or machine learning algorithms, we need training, and this is the training. So that's a remote sensing framework. So in this case, we used optical data from both the public sectors, such as Landsat 8 and Sentinel-2, but also private Worldview 3. So this comes at different resolutions. So around 10 meters for ESA satellite and 1.5 meters for the Maxar one. Now the approach is a pyramidal one. So specifically, we have used public available data in the bottom of the pyramid here, and we explore this deep learning framework to derive, let's say, the areas that is broadly speaking around the assets. So this is also called macro localization. And then we use a crowdsourcing approach or collective intelligence, so manual work, to derive the exact location of the asset and several other parameters in this top part of the pyramid. Now, if we start from the bottom, so this is the deep learning bit. So we used Sentinel-2 RGB band only, and we tested several architectures to get, you know, the location of the assets, and the best results were with an architecture called DenseNet. We optimized in this case on recall, so that means that we were looking for the maximum amount of assets. We deployed this model over China, so we see China over here, and in green you see all the footprints of Sentinel-2 footprints, which are quite a lot. So China is a huge country. We deployed the models within one of the partner platform, Astrea platform called Earth AI. And we got around 400,000 chips here. So we are working on chips. So deep learning algorithm require like to segment the image and to bring to use like chips into the architecture. So in this case, they're 300 by 300 pixels. Around 400,000 of them have been scored depending on the probability of having a cement plant. So probability of 0 to 1. 1 is the highest probability, obviously. Once we got like those chips like tagged in terms of probability, we then passed these to the collective intelligence team, which are basically image labeler. That's what they did was, you can see this here. So it's basically segmenting the image and detecting the plant, detecting the location, but also annotating excuse me, annotating some parameters such as the kiln. So the kiln is this feature here. Why the kiln? Or we see in this case here several kilns. So why the kiln is important? Because we can associate the kiln with the capacity of the plant. So we built specifically a model. So we see an example here where we have the kiln dimension and the capacity of the plant. There is a correlation between the two. There is a positive correlation. So the capacity parameter that is like annotated in the database, it's derived in this way. So this brought to the derivation of the final data set, which is shown in here. So the data set is composed by 3,117 plants, which account for about 90% of the global production. We validated this data set. Again, that was a huge manual validation. And we have seen how we capture about the 88.9% of the total cement capacity with continent statistic within the 5% of the error. Now, this was just a brief demonstration on the use of Earth observation and artificial intelligence for Earth observation, or AI for EO, within the financial sector, and in building a database like a geo-asset database, which, as written here, are quite important to assess environment-related risks and their exposure and the diffusion of these risks through the financial system, as I've shown in my first slide. We publish also this work. Actually, this is under review, so the reference is here. And yeah, this is the conclusion. So thank you for your attention. Contacts are in here. Thank you.
Thanks, Christian. We'll move on now to our final speaker before the panel session, and I'll hand over to William Bell, who is the Chief Technology Officer at Hyperfine. So I'll hand over to you, William. Thanks.
Hi there, guys. I can't turn my video on because it was turned off earlier. Could that be re-enabled? Thank you. So I'm just going to share my screen. Sorry. All right, so you should all be able to see now. So yeah, so I'm Liam, I'm the CTO of Hyperfine, and I'm going to present today about Climate Trace, which is an organization we co-founded in 2020, which focuses on the measurement of greenhouse gas emissions for every sector on the planet, using a mixture of satellite data and artificial intelligence. As a brief primer to my background, I was formerly an academic, and then I started working with Hyperfine on projects related to Earth observation, and the business actually focuses around the use of Earth observation data and natural language processing for understanding what happens on construction sites. But then we did a project with the European Space Agency to technology transfer that to the quarrying and mining industry, and that's how we got to co-founding the Climate Trace Consortium with 10 other organizations focusing on measuring greenhouse gas emissions for every sector, with sector specialisms, including power generation, transport, heavy industry, manufacturing, agriculture, shipping, fires, everything really, as well as the former US Vice President Al Gore, who supported us in July of 2020. So how does it work? We use computer vision to understand the time varying predictors of emissions. So for example, that's the activity level at a power plant. So you can measure the relative plumes that are coming from gas turbines using optical imagery. And because we have training data on what the emissions factors are relative to those plumes, we can then forecast what the emissions are in a timely manner, essentially. So that's what you see there in natural gas. But for example, our focus, mining and quarrying, we are able to use coherence to understand the changes in vegetation that indicates where the amount of production capacity based on the movement of plant machinery, which is the key driver of emissions in mining, aside from methane and coal. So this is kind of a list, an incomplete list of some of the ways that we do this via machine vision. So working out the infrared plumes from cement plants, for example, can be used as a proxy for production. The changes to cooling water, as I mentioned, changes to vegetation, burn indexes, depends on the sector really, but it's one way that we're able to generate independent facility level emissions data that we can then use for radical transparency. So how much emissions are cement plants responsible for, road transport, and the like. And this can actually get, but thanks to the spatial granularity that satellite data offers, we can then generate very temporally granular emissions estimates. So what you can see here is an animation of monthly level coal plant emissions in China from 2016 to 2020, which is the kind of radical climate transparency that is very difficult to achieve, but allows us to see the changes in activity over time in that subsector. And that data is actually published as part of Transition Zero, one of the power plants partners for Climate Trace. So you can read it at that link there. I'm sure the slides will be provided afterwards. But the purpose of doing what we're doing is to do it for every sector, because one of the issues that there are with UN emissions inventories is that there are sectors that aren't included, and they're not reported often enough to allow for rapid change. But this kind of gets into how every sector requires a different approach. So using those time varying predictors again, we can work out like what the actual usage is for roads, and then we can bring in other data as well. So because we know that there's a population of this number of drag lines, for example, on a coal mine, and we know the kind of activity it would take to get to that production level, we can then estimate emissions that way. It's fairly interesting, but the same applies for shipping, for farms and forest fires, and for ground transport, and for every other sector that we do. But once you get that inventory of facility level emissions, we can then aggregate up, and this is all available on the Climate Trace website at climatetrace.org, and develop an independent emissions inventory for every country, which we released in 2020 for 97%, I believe it is, coverage that we have in terms of sectors, and 100% of the world's countries reported at a sector breakdown level. So pulp and paper, aluminium and manufacturing, and then in mining at the moment, we've got copper, iron, bauxite, rock and sand, and we also have coal in there as well as a solid fuel, oil and gas, the lot. And the reason that's important is that if we can develop independent emissions inventories, we don't have to rely on self-reporting, and we also don't have to rely on the speed that countries move at, i.e. at the moment, emissions inventories are reported. Well, most countries haven't reported on emissions inventories since 2015, and they're generally incomplete and they're aggregated up. So you don't get that level of granularity that I believe you need to make radical change. So this kind of gets into it. So there's massive undercounts in, for example, plastic waste burning. There's also indications of undercounts in coal mining for methane, and the uncertainty intervals that exist in those sectors are massive. But if you have an independent emissions inventory for every country and for every asset, then you can hold governments to account. And also, as we go forward, we want to move down the spatial granularity so that we can do regional level emissions reporting. Because and there's a project that we have running with the climate group. But I really believe that state level governments have the capacity and also the political will to make change, even if when their national government does not, because they're closer and more accountable to their people. And it kind of gets into the principle here of what we do, which is that this data will be free and open for everyone to be able to address global emissions and to hold countries and hold companies to account. Yeah, so I was kind of giving a lightning talk, so I only got 5 minutes. So thanks for your time, and yeah, you know how to contact me there.
Thanks, Liam. So that concludes our 5 speakers for the first part of the webinar this morning. So many thanks to all of our speakers. I think that gives a really great overview of many of the key issues associated with space-enabled net zero. So the next part of the webinar this morning is the panel discussion and Q&A. And for that, I'm going to hand over to my colleague, Dr. Giles Bailey. So I'll hand over to you, Giles. Thanks.
Yeah, thank you very much, Colin, and thanks a lot to all the speakers. It was a really interesting, set of presentations. So we're gonna start by some questions. So I have first some more general questions that are open to everyone if you want just to touch on it. So the first one is some of the presentations touch a bit on on what kind of data you are needing or what kind of data you are able to produce. But I wanted to have maybe some more direct list, like a wish list, for example, of which kind of data you would like actually to be able to have from of observation sources, or maybe which kind of data you are able to produce and you see a potential, but you don't see any stakeholder really using them as much as they could. So does any of the speakers have something to contribute to this open question? Yes. Please feel free to just unmute yourself and talk to answer this question.
Thanks, Charles, and thanks for that question. I think this is essentially a question about what are the barriers to implementation of really good data, and from our perspective, we're finding there's quite a lot around data capability for storage, for processing. There's quite a lot in international arenas about legislation and how you report internationally on EO data. It's quite difficult to do this without stymieing innovation. That doesn't mean we shouldn't try and we shouldn't start. There's some really excellent work by the WMO to start to do this this recently, to look at international standards in EO data. And I think that's worth something pursuing and carving out space for doing that. And I think also it's about telling the key users that EO can do what they're already doing, but probably for cheaper and better in many cases. I think that there's certainly a role for education and informing, and we're working very closely with our policy leads to ensure that they've got evidence leads assigned to them that can upskill them on the latest innovations. So there's certainly a role for communication and education in there as well.
Okay, thanks a lot for your answer. Do we have any other contribution to this one?
Maybe I can mention that within the financial sector, or what I have shown was trying to use actually all the available data towards possible data towards deriving those sort of data sets in both the public and the private sector. But what I'm seeing is actually that there is a need for this, because private companies such as the one that Hartmut was mentioning, GHGSat or Satellite Applications, that are like actually new companies out of the market, they're trying to get this sort of data that maps like atmospheric components at a resolution that then is like suitable, for example, those financial markets. So looking directly at the assets and the methane emissions from plants, for example, or the temperature of a specific asset. So we are talking of breaking a resolution that was usually, this has been explained by the way, but usually around a kilometer or more into the meter one. And it's happening. It's happening right now with few companies, but this is the trend, and it's very good for our sector.
Thanks for that. We're gonna jump to another question. So we have a question in the chat from Emmanuel Mondon. To all panelists, is there any link synergies between your activities related to net zero and the various ongoing data sharing initiatives, being common European data spaces, Gaia-X, or others?
So maybe I can take some of that on. I wasn't a speaker earlier, Clement, and I also work with Clement at the ESA Climate Office. We are tag teaming another meeting at the moment. So I seem to have been renamed to Clement, but my name is Claire McIntosh, and I'm also a climate application scientist. So in terms of data share initiatives, this for ESA analysis ready data, getting the data out there in a sustainable way is clearly very, very key for us. There are lots and lots of components to that. I'm not too familiar with the specific data sharing initiatives mentioned here, but all the Sentinel data is free to use. It's publicly available. The derived products from CCI, the ESA's Climate Change Initiative, are the same. And we also have spent a number of years with CCI developing operationalizing that data. So we're a research program, but once the research has been done, we go to the Copernicus Climate Change Services to operationalize that data. So Hartmut's greenhouse gas data is available from the Copernicus Climate Change Services on an operational basis. And a key part of that process is also to understand what the users need in terms of uncertainty, in terms of spatial completeness, in terms of what does near real time mean in different sectors. It can mean very different things in different places. Subsetting data for local applications versus global applications, things like that. So yes, we're very engaged with large parts of the community on data sharing. It is hugely important for data uptake for us, and we're always interested to hear about user needs and requirements.
Thanks a lot, Claire, for your answer. It's really interesting. I have a question for Elsa. So you mentioned in your conclusion slide that one of the things that you needed was trust. And when we see that societies are getting more and more conscious about climate change risk and the necessity to change what we are doing and why what you are supporting is really important, I wanted to know if you would recommend certain processes or accountability measures, for example, like the aggregation tool that Liam presented earlier, to be able to increase public trust, as the trust is actually, a two-way street.
Yeah, so a trust is a very succinct way of pointing to things like calibration, validation, standardization, and also education of the users of the data. So that was kind of what I was implying. But I think in terms of examples of doing it well, I think it's about getting the users involved at a very early stage. And throughout the process development, we've seen some great strides made in GEO, the Intergovernmental Group on Earth Observation, to do this, and particularly involving diverse and inclusive communities in that. So to really consider future-proofing the application for your designed mission against the potential diverse future uses. So I think that's the sort of starting point. The other activities would be in the really complex processes of using Earth observations to derive things like concentrations and column densities, and then to do source attribution from them. We need a really clear critique of the algorithms and processes within that that we get through the academic community, but there's perhaps a missing gap in how that's interpreted legally and interpreted into policy making. So I think we need to work closely with legal bodies and with those very heavily involved with application on an operational basis to see how they do this to validate data against an evolving environmental backdrop. I mean, we're all environmental scientists essentially, and working with a really complex and evolving natural laboratory rather than a very controlled environment that many other scientists get.
Thank you very much for that. Hartmut, I think you have maybe...
Yeah, I just wanna add, because I think this is a very important point, and I think trust is really only possible if we have transparency and openness, and that people can verify results. And I'm speaking now for Claire. For example, the CCI program has really set the standard here how this needs to be done. But of course, this was much more focused on climate applications. I think now we are faced with a very quickly changing landscape, with many new players coming in, many commercial players which have not been, so much engaged with these ESA-style processes. And I think there's a big need of really trying to create new processes that allows also to bring especially the private sector into a similar, transparency framework, which often is a little bit conflicting, with IP and commercial interests. I think there is a big need here to sort this out.
Thank you very much for that, and I fully agree. So before we conclude, because we are running out of time, maybe Claire, do you want to give your last contribution to this question?
Yeah, just to reinforce what Hartmut says, I think there's a very big question about trust and traceability in the commercial sector is something that, relative to ESA, the links there are maybe not as good as they could be. I also think that traceability in particular, we talk about uncertainty and traceability and replicability in methods, that's going to become hugely important as we go from 2023 stocktake to 2028 stocktake. It needs to be very, very clear exactly how those uncertainties, how the data is measured, where the traceability chain is. On the large scale global data sets, that is a huge research question. And there are many, many people involved in that, but I think traceability is going to become very, very important going forwards in all aspects of this.
Thanks a lot, Claire and others, for the great answer to this important question. I see that in the Q&A box, Nicolas Lévesque has a question that is getting answered right now by text. So I'm going to jump maybe to another question before we finish by Emmanuel. So it's directed towards Elsa. Would a sensor attached to the International Space Station, similar to CO₂, relevant for monitoring agriculture metrics you mentioned in your presentation? So do you want to jump in?
Yeah, thanks. Yes, that's really interesting. I'm happy for you to pick that up with my team. I think when you talk about agricultural metrics, the remit is vast. So we're talking about emissions from agriculture in this context. It tends to be methane, N2O, ammonia, and to an extent local air quality issues from the processes around agriculture as well. So that's the types of areas we're interested in. But also, if you think more widely to adaptation, we're particularly interested in the intersection with what we can do about drought policies, about natural disasters, and that tends to lend itself to needing more high frequency, more rapid revisit times. Those sort of data sets tend to be more useful in things like the disaster risk reduction area that is more commonly associated with climate change adaptation. But I'll have a look at some of your links and do follow up with my team afterwards. Thanks.
Okay, thank you very much. I have a quick question for Liam. So I really actually appreciated your tool, your aggregation tool. And I wanted to know if so far in this project, you were able to observe some discrepancies between numbers announced by certain governments and your own data. And also if you are getting in touch with governments to discuss impacts of your tool or how to make it, more outreach of it.
Oh, yeah, absolutely. So on to your first point relating to potential undercounts, we have noticed some discrepancies in the data set for Japan, China, Sweden, and Russia in terms of undercounting in heavy industry and also in coal mining. Equally, one of the other frustrating things in the mining industry is that only 28 countries in the world report any mining emissions at all, which is, well, a ludicrous concept because, almost everybody mines. On your second point, actually, we are working directly with non-state governments. So the government of Jalisco and Querétaro in Mexico and Pernambuco in Brazil, the Basque Country in Spain, directly to build them their own regional emissions inventories, which in some cases is the first full comprehensive emissions inventory that they've produced to allow them to make change at that much more local level. So yes.
Thank you very much for that, Liam. So, we discussed about a lot of problems regarding climate change, things like that. But we've seen actually today a lot of fascinating presentations regarding wonderful science which is done the field. So I wanted to know if any of the speakers have maybe a positive note they want to finish on for this session.
I think this is a sector with really huge potential, and we've benefited hugely in DEFRA from serendipitous application of Earth observations that's not necessarily designed for us in DEFRA. So I think that the potential for application is vast. So do think wide, think policy application, and not necessarily policy design, but how do we verify delivery when considering what potential application we have. The UK is really well positioned in being an expert in both the upstream and the downstream sectors, and can go forward and do great things with Earth observation. So I'll certainly be keeping an eye on it from my new role, even though it's less EO focused. Thanks.
Thank you very much. Liam, you have something to add to that?
Yeah, so I guess I kind of wanted to say that to end on a positive note, there's a level of serendipity here in that we've had this kind of problem before. You know, we noticed the hole in the ozone using satellites, and we're then able to actually make impactful policy to mitigate that. And now we're hitting the exact same. I mean, you can see from every speaker here in GHG emissions monitoring, where once we measure it, human ingenuity is good at solving the problem, and I think that we will do it.
Thank you very much for this note of positivity. I really appreciate it. And with that, I wanted to thank you all for the questions, but also for the answer to those questions. And I will head to Eddie for the closing remark. Thank you very much.
Thanks, Gilles. So yeah, once again, we'd just like to thank all of the speakers today for their fantastic talks, and also for answering those questions. And thank you to all attendees for your participation and for asking those questions. There'll be another webinar in mid-July, which is the second one on this space-enabled net zero by 2050, and that one's going to be focusing more on sort of new opportunities and services. So yeah, thanks once again. We'll summarize what's been said here today with a blog post, and we'll attach the recording of this webinar and pop that onto the Satellite Applications Catapult's website. So with that, thanks again to everybody for their participation today, and we'll stop recording and end the call. So thanks all, see you soon.